Hello, so this is Emmeline for an overview of what I did last quarter on the Expedition engine. This last quarter was quarter 2 or winter quarter 2020. So I made myself a little PowerPoint here to hopefully keep me more on task. Here's an outline of what I want to talk about. I'm going to do an overview of the final project. I'm going to talk about our DX11 versus DX12 app. I'm going to overview the DX12 app, which is what I spent almost all of this quarter focused on. I'm going to talk about a few of the complications I hit with the DX12 app, and then I'm going to talk about what we finished up with, which was refining the particle system. So starting with that overview, we created a multi-thread DX12, DX11 app. You can switch between DX11 and DX12 using a macro. I'll go into that more later and show you the code for that. We create a much more efficient INSYS particle system where all particles of the same type are now in one draw call instead of per burst. And then I think the most impressive thing is we now have a solid DX12 app, or the most exciting thing is we have a solid DX12 app to build on for next quarter. So for DX11 versus DX12, they share asset managers. So let's go over to the code for me to show you this. So if I go into graphics, not the DX12 graphics, the regular graphics, because they use the same managers. And if I go into the model, for example, that's where the model manager and the texture manager live. If I then go into the model manager, when you load a model, let me close all my other tabs real quick. When you load a model, it takes you to the private function, and then that creates a new model. And then when you create that new model, when you load the data to the GPU, that's where the difference part is. So you can see most of the high-level API is the same and the stuff that the user will be interacting with, and we'll see that throughout. But then when we get to the point where we need to interact with the GPU is where the macros come in. So for a model on DX12, you create a default buffer for it. And so you need an upload buffer and a default buffer because the CPU cannot write directly to the default buffer, so you have to send it to an upload buffer and then to the default buffer. So they're both the same model class, but when you load the data to the GPU, it's different. And the DX11 model, if we come into the header, the DX11 model will have a couple buffers, D3D11 buffers, while the DX12 model has resources, D3D12 resources. But they still use the same class. It's the same with the texture manager. It's one texture manager, but then when you go to load the texture, you do the private load. And then if it's DX11, you just add a new texture, but if it's DX12, you also have to create the descriptor heap and then load the texture. You have to create a shader resource view and so on. If we go into new texture, it also is different here. In DX12, I use a different library and we can only do DDS files. We don't support TGAs in DX11 just because of the library I'm using. Yep. So the only asset, so that's the same for textures and models. But there is actually a different shader manager. If we come over here, so depending on whether or not you're in DX11 or DX12, the shader you use differs. That's just because I didn't compile them into one. They could in theory be compiled into one, but I just didn't do it. So when you initialize the DX12 app, it will initialize the shader manager 12. And if you initialize the regular DX11 app, it will initialize just the other shader manager. Yeah. So then we have specifically the 12 shaders. Um, and part of the reason is they need different input layouts and stuff. This could be done with the macros like they are with the other resources. But instead I did it like this because they need a few different functions, such as prepare to render and update texture are pretty different. So I decided to keep them separate because there are much larger differences than with the models and the textures. Additionally, you have to create a pipeline and such, which isn't stuff you need for the other textures or for the other resources, but the shaders need a whole different set of stuff. Yep, so I showed you that now a macro decides how things are initialized and used, but there are no major API differences. But it does look a little different when you actually run the program, and that's because of different shaders and different blending for the particles. So if we go into the user code, if I just go into this first demo, all the code looks exactly the same for the user. They still have the same graphics objects and such. Down here you can see that they set the worlds and they start drawing and such, and this doesn't change at all for the user depending on whether it's DX11 or DX12. It's all macros on our end that switch out how it's drawn. So the user doesn't really have a concept of DX11 or DX12 except for if you go into Expedition Engine Resources, go into the engine setting app, there's this true or false that makes it change. Yeah, so that's an overview of how DX11 versus DX12, the major differences and how it swaps in between the two. The next thing I was going to talk about is specifically the DX12 app and go into a little bit more detail about that since that's what I spent the majority of this project on. So as you can see here, these are the last 2 points I talked about, how a macro decides whether things are initialized and used, and how there are no major API differences. And then for the DX12 app, the first thing I'm going to start with is just going over basic app creation in the code. So if we switch back to Visual Studios here, and we go into my DX12 app, let's actually start where it gets called. So if we go into the engine class, when the engine starts up, you can tell we have several macros in here for multi-threading and several things. But here we have initialize DX12. You can see I have some things in here commented out. I'm going to delete those because they're not necessary. In DX11, you initialize everything here. In DX12, you actually do it in the app because order matters a lot more for these initializations. So let's go in here. So the initialize function is pretty hefty for DX12. You start out by finding the client rectangle, and then you have several things. You have to enable the device. So let's go down to the creation functions. You create a device, you create your fences. I've talked to you pretty heavily about what these things mean, so I'm not going to go into it too much. But we create a device, we create our fence. So this querying descriptors, every type of descriptor has a different size, and that size can vary depending on your hardware. So you have to ask your device how big these descriptors are. So this is where the information about different buffers are held, and that will let you increment through descriptor heaps later on. I create all my command objects. Here you can see I actually have 4 command objects. I have one for pre-render, post-render, and for the render command list. I'll talk about that in a second when I talk about the actual render loop in this DX app. I create a swap chain. I have my descriptor heaps for my render targets and my depth stencil view. Yep, so that's pretty much it for app creation. And if we come up here, let me look at my PowerPoint real quick. So then specifically for root signature and command list initializations, let's go all the way back up to my initialize function. So I create all of that stuff, and then down here I have an initialize engine resources. So this is where I actually initialize. So now that the device is all set up, I can initialize the assets. And the reason it's important that I do this inside of the app is if I come up here, it has to be done inside of this command list. So I do it up there, and then I come back down to the initialize function. This is also where I set the root signatures. So I have a root signature for all the color objects, and then for the textured objects, and then I have one for the particle objects as well. I'll get into later, but something interesting I was able to do with the particle thing, with the particle root signature, is it dynamically takes the number of textures into the shader resource view, which I think is pretty cool. So I have that working now where you can have an instant particle and each particle has a different texture. So I think that's pretty cool. And then I have a sampler and a few other things. So that's that on that. Let's look at the PowerPoint real quick. So the next thing, so the big things that took up my time this quarter was getting that basic app running. I spent quite a while in a app outside of the Expedition engine, just getting that basic DX12 app running. And then once I imported it into the Expedition engine, it was figuring out where to put resource and stuff. So as you saw, I have that root signature and several command lists in the DX12 app. And that's because you can use those same root signatures every frame. So if I come down, let's see where it is. Yeah, here. So before you render, you have to flush the command queue, which is essentially, yeah, so now I'm going to go into how a render loop really works. You have to flush your command queue first, which is, you have to make sure you're not too many frames behind. Right now I give it a total of 3 frames, so the CPU can run up to 2 frames ahead of the GPU. So here, if you're getting too far ahead, you have to wait. So after you do all the way back up to the render function, after you do that, you present your swap chain, which unlike in DX11, this assumes that you've already taken care of all the synchronization stuff, so it just zooms right through there. You update the back buffer, and then I reset my 3 command lists that are needed now, my pre-render, my render, and my particle. So the cool thing about this is the regular renders and the particles, their commands are created concurrently because they don't have anything to do with each other. So as I'm sure Sarah is going to talk about, the task graph allows a render thread and a particle thread to run at the same time, and they both get to create commands, and then they're submitted to the command queue. So then in the pre-render command list, I clear the back buffer and I switch it to present mode, and I clear the depth stencil, and then I close it. And then I set all the things I need for the render and particle command so they're ready to render. So they need to know what descriptor heaps they're pulling from, they need to know what their render targets are, so on. So then after that, the DX12 app goes into render, so that's prepare to render, and after that it goes into the render call, which just calls all of the shaders and all the particle shaders and adds all of those to the command list. And then once that's done, you have to fill in your post command list. So I have to switch the buffer back to a present target, and that's pretty much saying that's the only thing the post command list does. Ideally, this command list should be pre-created and not recreated every frame, but I haven't done that yet, obviously. Then you have to make sure all your command lists are closed, and so this is the real reason why it's so important I have a pre-command list, 2 middle command lists, and a post-command list, is I need to make sure that these 2 commands happen in between the outer commands. So if I was to put these commands into either of these commands, they could happen out of order. Now what I could do in theory would be to put the pre-render command list in the top of the render command list, and then the post-render command list into the back of the particle command list. Don't want to do this because in the future I would like to create these 2 command lists, the post and the pre, once at the beginning, and then never create them again. So that's an overview of how the render loop works in DX12. Let's look at our PowerPoint. So I just lost some of my footage because I forgot to switch windows, but I think I had just started talking about frame resources, so let's go ahead and jump into that. So if we come over here to my Visual Studios, and we go into here, you can see that the DX12 app has the number of frames as frame resources. For the number of frames, it makes frame resources, which it owns. Right now I have 3. I found that to be the best number. Much more than that doesn't seem to really improve anything. So that's where I have it right now, but I need to do further testing on it. If I go into the frame resource, this holds several things. So one thing it holds an upload heap, and that's where you upload the data for per frame buffer. You can see here I create an upload heap just for the frame buffer. Then I also have an entire instance buffer, and that instance buffer holds enough room for the max number of instances you can have for each of the different kind of objects. Then in order for the user to know, or in order for the shader to know where in this buffer, this giant default buffer needs to look, you create a bunch of instant buffer views. And so it's called constant buffer view description, and I create all of these for each of the different kinds of objects. And then when the shader, if I come over here to the color light, when the shader needs to prepare to render, it asks the GPU to get it the specific view, the vertex buffer view it needs. And you send that to the input assembler as a vertex buffer, so it has all the instance data it needs. You can also see that for the descriptor table, for instancing, the instance data goes to the vertex buffer, but the constant buffer information goes to the root signature. So that's where you send the frame data. So that is all held by the frame resource, as well as if we look at the top here, the command allocators are also held by the frame resource, because that's what actually holds the command information, so that cannot be deleted before the frame has been used, unlike as we saw the command list can be deleted before their lists have been used, because the actual information is in the command allocator. So the last thing I want to talk about in regard to the DX12 app is a little bit of what I already talked about. So I talked about how textures are all stored in the texture manager. They're in one big descriptor heap, so all the textures have one descriptor heap, and those descriptors point to the textures, which are stored in GPU memory. But then I want to talk a little bit about how I now have those textures working in instancing. So different instance models in one draw call can have different textures, and this was to address a problem I was having with upload buffers, because upload buffers update instantly because the CPU has direct write access to them, and so it's not done through a command. So this led to some overwriting of data, and the way I fix this with the regular buffers is default buffers update by command. So now I put the data into an upload buffer, and then the upload buffer in a command list gets copied to the default buffer. So let's go ahead and look in here to show you what I mean. So here you can see when you send particle data to the GPU, it's on the command list, and you copy a buffer region. And so the actual upload buffer lives on the particle in this case, and it passes in its resource, which is an upload buffer. And then I do the copy on the command list, and it happens at the correct time now. So I was having a similar issue with textures, where if you had two texture objects, the second texture object would overwrite the first texture object, or vice versa, depending on the timing, or vice versa. So I had to create a way for textures to be stored on the particle themselves and not in a bigger heap. So the way I did this is if we actually go over to the particle shader in here, you see here it has an unsigned int at the very end that says texture. If I go ahead and open up the particle, it's in here, the particle shader, I'm now passing in, and this is, so in HLSL model 5.1, you can do this where you pass in an array of an unknown size, and then using the input text name, which is the semantic instance texture, you can index into that array. And so so somehow I have to make the shader know where this array of textures is, and it can be a dynamic size. So the way that is done is in the texture manager, like I showed you earlier on. If we go in here to the texture manager has a resource heap that's of the same dynamic size number of textures. So whenever a texture is added into this, you update the descriptor heap. So this essentially copies the big stack of descriptors we have in the texture over into the descriptor heap that's used by the shader. And then, so this is copied into the shader, and then if we go into the if we go back into the particle shader, when it renders, it just gets a pointer. It gets a pointer to where that stack of textures is. So the root signature doesn't look any different, except for now, instead of just pointing to, now it knows that instead of pointing to one texture, it's pointing to a list of textures of an unknown size, and then the shader can index into that. Well, the CPU knows the size, the GPU does not know the size of the textures. So I think that's pretty cool that you can send an unknown number of, it's basically shader resource views to the shader, and then you can dynamically index into it. Let's see, what is next? Yep, so I don't actually have that texture fix in the texture and texture lights yet. I just put it in the particles actually today. So that was pretty exciting. Next. So the particle system, as I showed you, it sends the world. It also, let's go back over here. It also, you send a tint, which is cool, so you can tint your particles. I'll show you a demo in a second for all of that. And then you can also get the texture index. I did some fun blending stuff. So I'm going to change this blend factor to a user-facing variable later, but you set a blend factor, and so that allows to get a nice particle effect where it looks more like flames and like the particles fade into the background. So that's pretty fun. I've been working on that recently. Down here you can see you have to set the blend state, and you set it to the blend factor. You can also set to the inverse alpha, the alpha of the source or the destination. So all that good stuff like it was in DX11. What next? Oh yeah, and then one last thing that was pretty cool that I got to implement, if we look at the PowerPoint, is since we're doing the blending, I am sorting the particles so they render back to front, so the front doesn't blend into the background, they blend into the particles behind them. So all the tests we've been doing, all the performance tests have been using this sorting, and I'm actually using a priority queue that Sarah made for the alarms. So let's go into the particles and render particle type. So only the types are sorted, they aren't sorted in between types, so that leads to a little weirdness, but not too much. So every time you have to render, I'll show you in DX12. You go through all the particles, you add all of them to a priority queue, so you pass that down to the types. The types add all their things into it, and that's automatically sorted as you add. So I'll show you in here. When you add it in, you push to the front, you push in the priority, so from that it's the distance from the camera is the priority, and then that sorts it all nice and efficient as you add it, and then you just pop from the front and you render it, and you copy it into that map resource into the upload buffer, and then later on when you go to render, that upload buffer is sent to the GPU. So that is all pretty cool. So here's one of the little demos I made. So it's just to show off the particles a little. I had a pretty fun time making the particles look nice with the blending. As you can see, there is a little bit of an issue where if you're on the wrong side, it's clear that the particles aren't entirely in order. That's because these are 3 different particle types. Um, they could be fewer, but that's just how I have it right now. Yep. And so there they are. You can see the nice blending at the top. They blend in with the background a little. And then if I go ahead and exit out of this, we go over to Visual Studios. That's running, even with the capture on, that's running well under 30 frames a second with a bunch of particles on screen. If I actually go ahead and run that again, I can see exactly how many particles we have on screen at a time. That's DF12, my bad. So this is for one of the 4 types. So that one has 1,000 particles, which means it's probably a total of, well, now they're all dying because I put a breakpoint now, aren't they? Yep, so it looks like that's around 4,000 particles on screen right now. In our other demo, we had I'll show you this data in a second, but we had, I can get around 350 bouncing balls, each with around 14 particles on them at a time, so that's around 4,000 to 5,000 particles, and we can still get 30 frames a second on that. So that's a big improvement from last quarter. I'll go ahead and show you those numbers now. So here's some of the data that we've collected over the past 2 quarters. So this is the really impressive bit. This is from last quarter. We have single-threaded versus multi-threaded. You can see here that we'd be getting above 30 frames a second with about 30 balls on screen. These didn't have that many particles each. Unfortunately, we didn't record the amount, but I can't imagine there were more than 1,000 particles on screen at a time. The main problem with this system, though, was every single burst of particles was creating a new draw call. Let's move on to the next slide. And we'll see here that we can get close to 400 balls on screen. Each of these have around 14 particles at a time. It takes us to well over 4,000 particles on screen at a time, and we can still stay at 30 frames per second. There are a couple things that really helped us get here. The first was moving the particle system we came up with that Sarah did most of the job implementing the systems for, was that all of our particle data is now shipped in one big instance buffer per model, and that can all be instanced in one draw call. We had a slight limitation on that, was I didn't have textures ready, but as I've discussed earlier, I now have the ability for there to be multiple textures in one instance call, so this should only even get better next quarter. Yeah, and then additionally, we moved all the graphics object data next to each other in memory, so we're getting much more cache hits, and that also contributed to that. The next slide I have is just something I thought looked kind of cool. It's a pretty weird looking slide, but this is the same slide as the previous one, except for it's frames per second instead of seconds per frame. Yeah, and then the last thing I'm going to show you is I'm just going to show you the other demo. So here, let me take this. Let's switch over to Visual Studios. If you want to see these demos yourself, you have to go to Expedition Resources, go to the Start Game, and then so that particle demo I just showed you with the particles coming out of the bases, that's scene particle demo, and then if you want our bouncy ball scene test, to move around the scene, it's actually I, J, K, and L to move the camera, and the arrow keys to rotate it. Here, and then this is the bouncy ball demo. Oh, I forgot I made the particles smaller. There they go. I think I have a few more balls on here right now than my computer can handle. Yeah, but to see that, I turned the texture size down for my other demo. I'm just having them use the same model right now. But for that, if you go into load resources and you turn this up to 4, that changes the model size. You could have multiple sprite models, but I do not right now. Here, let me launch that and then let me switch over to the game capture so you can see it. There you go. A little slower with the capture going, but still pretty cool to watch. And I believe that's all for me for Expedition Engine. If you have any other questions, let me know. Um, yep.